and I'll see if I can record this in any sort of decent quality so that those people who haven't joined or won't join or aren't here can share it later. So, one or two sort of fundamental things. Equilibrium, right? Can someone explain to me what equilibrium means in terms of forces? Have you heard that phrase before? That is when sort of a chemical reaction reaches equilibrium, I suppose. In terms of forces, equilibrium means that everything is balanced. So if you've got something that is in equilibrium, in effect it will be at rest or travelling at constant velocity, because there'll be no resultant force, or the resultant force of all the things acting on that body will be zero, so it won't go anywhere or do anything. Right? So if I've got something, a body that has forces acting upon it, so it could have a force acting in that direction, one in that direction, one in that direction. If that is not moving, then we know that all of these forces are balanced. This thing is in equilibrium. And so if I add up all of these forces, taking into account their directions, then they will add up to zero. So they're balanced. Now, this is a mathematical way of writing that. So we've got vertical components of forces, we've got horizontal components of forces, and we've got moments. So there are three conditions for equilibrium really. You've got to have your vertical forces, or the vertical components of your forces, they've got to balance, and your horizontal components have got to balance, and all add up to zero. And also you can't have any moments in there as well, because if there was forces not acting at a single point but acting at two ends of a long thing, a long body, not just a point but an actual component, so you had a force acting this way and a force acting this way, if that force and that force were equal and opposite, then that would fulfill these two parts of the equilibrium, because they will balance each other, so it wouldn't move anywhere. But you can see that if I get a lever like this and apply a force on one end and apply a force on the other end, then there's a turning effect or a moment, and so this thing won't move, translate anywhere, but it'll spin round. And if it spins round, then it's not in equilibrium because it's moving in effect. Now we don't actually come to do much with these at this level or in this particular unit, but there are another set of more complicated sets of forces and turning moments that you can do, where you have to work out the resultant force and the resultant turning moment and the distance of that turning moment from the line of action and all that kind of stuff. But we don't have to do that. You'll be glad to know. But we do need to have a good understanding of what equilibrium is, because there's a few questions and a few problems that I'll be showing you in a second. So you'll need a pen and a bit of paper for this. And also, what we were doing last time, any force, so I've got a force F here that just happens to be going straight up at this angle, you can sort of divide that force into a vertical component and a horizontal component. And that's important, because if you've got more than one force acting, it's very difficult to add them up to take into account their different directions. So what you have to do basically is what's called resolve forces. So each force in a system is resolved into its vertical components and its horizontal components, and then you can very simply add those two sets of components up and come up with your resultant fairly straightforwardly. Now, we did cover this last time, so hopefully I won't be telling you anything stunningly new to you, but it's just a quick reminder that in this particular scenario here, where that theta is that angle there and that angle is known, then if this is the force F, then if I want to find the horizontal component where I'm going through the angle, so I'm going from this line and I'm coming this way, so I'm actually going through the angle that I know, then FH equals F cosine of that angle, cosine theta. And the vertical component, if that's the known angle, starts to move this way around, so it's actually my force arrow, if I rotate it, is moving away from the known angle. Well, that will be F sine of theta. Now these aren't fixed. These are only true if you've got this particular scenario and this particular angle. If I was to change this so I had this angle, then these cos and sines would actually flip over. So instead of trying to remember this, because it only relates to this one example where this is the angle that we're talking about, it's best to try and remember that if you want to translate or resolve a force through an angle, then you use the cosine, and if it's away from the angle, the known angle, then you use a sine. And we'll sort of come to that when we do some examples in a second. There are another couple of definitions that we ought to just cover that is going to be on this first set of sort of worked examples as well. So in part of definitions we've got resultant and we've got equilibrant. And they're a couple of different types of forces. So if you've got some forces acting, so you've got a force acting up there, say, and you've got another one acting over here, you can determine what the resultant force is by drawing your old parallelogram of forces, and that there would be your resultant. So that is a resultant. And this would be an instance where this system isn't in equilibrium, because if it's got a resultant force, then obviously these rules aren't true anymore, because if it has a resultant force going in a particular direction, then it'll go in that direction. So the sum of the forces acting on that point won't be zero, so it will be shifting. And that's the whole point of an equilibrant. So an equilibrant is a force that is opposite and equal in size to the resultant. And the idea of an equilibrant is that it will supply the force that is going to bring this system into equilibrium. So if you've got two forces acting that way and you're trying to find the force that you need to apply to rebalance that system, first of all you'd calculate the resultant, because that's the effect of all of the forces in that system just being replaced, all of the individual forces, with one resultant force that's the equivalent, and opposite and equal to that would be the equilibrant. And the equilibrant, if you added that into the system, would bring this system into equilibrium. So it would balance everything out and stop everything from moving. So we need to know those two definitions of what things are. And I said I'll try and get this videoed and sent through to you. So, question time. So determine the resultant and the equilibrant of this system. What is here? So, you know the angle and you know two forces. So we don't have to resolve anything in this case. It's a fairly simple method. Because these are at right angles, it's nice and easy. We can sort of use Pythagoras. So if I complete this, what would be a parallelogram of forces, but now it's like a rectangle of forces, because it's at 90 degrees. And I know that if I was to draw this out on a piece of graph paper full size, I'd be able to measure these things with a ruler. And so if I had 12 centimeters that way, 14 centimeters that way, and then completed this square and then drew the diagonal in across there, then if I measured that, that would be the magnitude of my resultant, and if I measured that angle there, that would be the direction of my resultant. But we're going to work it out using maths, and we can work out that quite straightforwardly using Pythagoras, because we know that that's a right angle there, because if that's a right angle, that must be a right angle, so must that and that. And so I know that this dimension of this triangle here, if we just redraw that triangle to make sure everyone can see it properly. So that's what we're after. That is going to be our resultant force there. I'll call that resultant. We know that that's a right angle, and we know that that height there is 14 kilonewtons, and that left across there is 12 kilonewtons. So quite straightforwardly we can use Pythagoras to work that out. So we know that in this case r squared equals 14 squared plus There's a hole in my desk, squared, 12 squared. And so we can add those up and find what r is. Now we also need to be able to find theta. And we can sort of intuitively know that if this is 14, if that was 14 as well, then this one will be at 45 degrees. But we know that it's not that because they're different sizes, so our angle here will be different. We would expect this angle to be smaller than, or would we? Depending, actually, if that's only 12 and that's 14, which way would it be? This angle would be smaller than this angle. So we're expecting this one to be over 45 maybe, and we'll work it out. So again, basic trig this time. And then what have we got? We've got a hypotenuse, and that's what we're trying to work out. We've got an opposite and we've got an adjacent. And so we can do the tan of the angle, can't we? So I know that tan of theta equals 14 over 12, and so I can calculate what theta is. So get your calculators out and just do those two quick sums for me, please, and tell me what theta is and also what the resultant magnitude is. And I'm getting you to work it out for a number of reasons. A, to make sure you're still awake, and B, because my daughter's stolen my calculator. So 49.4, that sort of thing goes in with my impression that it's going to be a larger angle than 45, so that's probably true. What did you get for the R? 300. We've got 14 kilonewtons and we've got 12 kilonewtons, and you're saying that this one's going to be 340 kilonewtons. I'm pretty sure you did too. Yeah, if you look at some of these things, don't just accept what your calculator spits out. That should have been screaming at you that, hang on, I can't suddenly convert 14 kilonewtons and 12 kilonewtons into 340 kilonewtons. That just doesn't scan. So I get the square root of that, which is 18.44 kilonewtons. Okay. So if I was to describe that resultant force, I would say the resultant has a magnitude of 18.44 kilonewtons at an angle of 49.4 degrees above the horizontal. Now, if I was to calculate the equilibrant, what would that be? What would the magnitude of my equilibrium be? We've got a resultant going in that direction. We've got an equilibrant now. I want to know the size of the force that's going to balance this resultant. So what's the magnitude of that equilibrant going to be? Have a guess. It's exactly the same. It's the same but in the opposite direction. So the magnitude is going to be the same. So it's going to be 18.44 kilonewtons, but the direction, if we want to cheat, I suppose we could just say opposite the resultant. Okay, it's probably the easiest way to describe it. Otherwise, you would describe it as at an angle from something. but it's fairly obvious. If you've got a nice little picture in there, then in a direction opposite the resultant should be all right. Now you will need to be able to do that to determine the resultant and to then state what the equilibrant is, because you will know that one is the balancing force for the other. So this one is a whole lot trickier, but the same or very similar question. So the resultant and the equilibrant of this system is a bit more complicated. So in this case, we've got to resolve this into a series of vertical components and horizontal components. Then we've got to draw an equivalent system consisting of just two forces, one vertical and one horizontal, and then we can do the same thing we did before. So the idea of these is this one's only got two forces in, this one's got several in, but effectively it's the same methodology behind it. It's all about determining the resultant. It just gets a bit more complicated, that's all. Now the first thing we can see here is that we have some angles that are given, but the angles that are given leave us having to work a few things out, because what we're going to have to do here is find what the sum of the vertical components are and the sum of the horizontal components are. So we'll do that in a second, but in order to do that we need these angles. So these are the given angles. 85 is fine because 85 is in comparison to like the horizontal, so that's a useful angle. These ones are less so. Right, so what we really need is that angle there between the horizontal and there, and we need that angle there between that force and the vertical, and that angle there between that force and the vertical. So currently the sum of those two is 60, and the sum of that lot is 135. So that angle there, for instance, well, that angle there, what size is that angle there? Just that part of that 135. Yeah. Which leaves us with that one, which must then equal what? Yep. And then we've got this bit. Yep. And this bit. Yep. Right, so don't sit there struggling, scratching your head about these big angles. You need to be able to just write them in. And it's all a matter of saying there's 90 degrees in a right angle, and you can work them all out from there. Now this gets a bit more complicated because we're actually going to resolve forces now. So we're actually going to use this stuff about how to resolve into horizontal and vertical components. So what we're going to do is we're going to consider each force in turn, and for each force we are going to determine those two components, or rather we're going to do all the vertical ones first and then all the horizontal ones. So there's four forces, so this is going to get a bit complicated, so you might want to follow this on a bit of a pen and paper as we're going. So let's start with the sum of the vertical forces. So all the vertical forces. So this 30 kilonewtons here, this is going to have some vertical effect, and that vertical effect is going to come here. I'm going through the angle. Remember our little rule of thumb, that if you go through the angle you use the cosine. So I know that my component of that force in the vertical direction is going to be 30 times the cosine of 45. So that's that one. Let's have a look at this 60 kilonewtons. The vertical component of this 60 kilonewtons, any ideas what the vertical component of that's going to be? You don't have to work it out. It would be 60 cos 90, but what's the cosine of 90? I don't know actually. It should be a 0, shouldn't it? Let's have a look. cosine of 90 is 0. So there is no, and that kind of makes sense, there is no vertical component of this horizontal force, because if something's horizontal, then it's having no effect whatsoever in the vertical, so you don't get anything. So that one, you can either put in 60 cosine 90, but you don't need to, because you know that's actually going to be 0, because the cosine of 90 is 0. And it's horizontal, so it has no effect in the vertical plane. Do you get it? Right, so let's carry on going round then. Now I've got 20 kilonewtons here. So I've got a choice now. I can either use this angle or this angle. But what I'm going to do is I'm going to try and use lots of cosines, I think. So as long as I've got the size of the angle that I'm going through, I can use cosine. So this 20 kilonewtons is actually going to be in the opposite direction of that one. That one's going upwards. This 20 kilonewtons is going to have an effect downwards. So it's going to be minus. That's the positive direction. We ought to really say that. That's the positive direction, and we'll have that way as the positive direction of the horizontal stuff. Positive vertical, positive horizontal. Okay, so because that's coming down, then I'll say it's minus 20 kilonewtons cosine of 5. And this 90 kilonewtons here is also coming down, and I know that's 55 degrees, and I'm going through the angle again, so it's minus 90 times the cosine of 55 degrees. Right? So that comes up to, I'll let you work that out in a minute. So that's the vertical components, and if you add all of those together, then you get the effective, you can replace all of these with one single equivalent vertical component by adding them all up, and we'll do that in a second. But let's get all of the force horizontal components this time. And again, we're going from left to right as positive. So we've got that one, and that is just going to be 60 kilonewtons because there is no angle because it's directly in that direction anyway. And that is going to be plus this 20 kilonewtons, because it's on this side of the center line, is going to have some effect in this direction. So that's going to be 20 times, if we put it through there, the cosine of 85. Or I could use the sine of 5, because I'm moving away from 5, but I'm actually moving through 85. And you'll find that the cos of 85 is the same as the sine of 5. That's just how the cosines and sines work. So it doesn't matter which one you use, as long as you use the right ratio. If you're going through the angle, use cosine. If you're going away from the angle, you can use sine. So it's either cosine of 85 that we're going through, or it's the sine of 5 that we're moving away from. And these two forces then, these will be working in from right to left, so there'll be minus ones. So in this case we've got 90, and we're winding up, so we're going away from that 55 angle. So that's going to be sine of 55. And we've got this 30 kilonewtons, again it's going to be going in this direction, so it's a minus 1, and that too is going to be rotating that way away from the known angle. 30 sine of 45. Right, so work those out for me and add them up. So I want to know what the total vertical components are, and I want to know the total horizontal components, please. Anyone got an answer for the first one yet? I got that as well. Minus 50.33. And these are in kilonewtons, remember. You have to get your units right. Does everyone agree that it's minus 50.33 and minus 33.19 kilonewtons? Oh, Drew's giving me the thumbs up. So what do we do now? Well, we've now got two forces that if we apply to this system will enable us to replace all of those forces that are currently working. But we need to be a little bit careful, because if we remember our positive directions, so we said that one is going to be the positive vertical direction, that one is going to be the positive horizontal direction, and both of these ones are negative. So we're going to have a vertical component of this force now that is acting downwards that way, and that is going to be 50.33 kilonewtons. And we're going to have a horizontal component going in the negative direction, and that's 33.19 kilonewtons. Okay, so all of a sudden now, that horrible complicated system of 1, 2, 3, 4 different forces all acting at different angles, we've simplified it into two different forces by being able to add up all of the vertical components and all the horizontal components of everything. So we've simplified that system down into two forces, which turns it into this problem again. All right, so now it's simple. What we need to do now is calculate the magnitude and direction of the equilibrant and resultant. So we'll start by calculating what the resultant is, and then by implication we'll know that the equilibrant is opposite in the same magnitude but in the opposite direction. So what I'd like to do, please, is work that out and give us a shout in a minute. So we've got two forces there, and what we're after is ding 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 ding, complete that parallelogram of forces. What we're after, please, is the size of that resultant. So you work it out for me. And we also want to know about the direction, so we need to calculate that angle there, theta. So if I was doing this, what would I do? Well, I'd say that r squared equals 33.19 squared plus 50.33 squared. And then I'd work out that, I'd find the square root of it, and I would find that r equals, does anyone calculate that? Okay, so the resultant is 60.29 kilonewtons. And the direction, we need to find that angle theta, or ostensibly we could find that angle, or there's lots of ways you can define direction. You could find a bearing from that all the way around from the from a direction going positive. As long as you've got a drawing, a sketch, and you've got an angle, you don't necessarily have to describe it in words if it is actually described in your sketch for you. So I probably define that angle there. And let me know when you've calculated what that angle is. You've got a triangle that you can draw out again if you'd like, and that's 33.19. That length there is the same as that length there, so that's going to be 50.33. You know that angle there, that's a right angle. How are you going to find what theta is there? That's your hypotenuse, that's your adjacent, and that's your opposite. So theta would be tan to the minus 1 of opposite over adjacent, 50.33 over 33.19. Because tan of theta is opposite over adjacent. And then you can work out what theta is. Do you agree with that? Sometimes I do make daft mistakes when I'm doing these. As we are prone to do.
I got 56.6.
So did I. So direction where theta equals 56.6, and then if you want to describe it in words, you might say from right to left, 56.6 degrees below the horizontal, or something, or just draw a picture is usually the better way of doing it. And as long as you've defined what that angle is, then it's fairly straightforward to someone to work out what the right answer is. Okay, so go back to the question, what we're after. Determine the resultant and the equilibrant. Right, so what's the equilibrant is going to be? Well, the equilibrant is going to be up there, and you might want to add this to your drawing as well, because these questions really should be accompanied by sketches. Equilibrant, or you might, if there's a sketch in the actual assessment already, you might just add to it and annotate it. So what's the resultant? So the resultant is that direction. That what's the magnitude of the equilibrant? Correct. Exactly the same size in terms of magnitude as your resultant, but it's in the opposite direction. Okay. Equilibrant is 60.29 kilograms in the opposite direction to the resultant. Whoop. Okay. So important bits, there's all that bit, that's the solution there, and that is your answer to those two bits of that question. And this way of resolving forces into these vertical and horizontal components and then being able to add them all up is a common theme that which will develop through a few more worked examples that we've got to go through. These questions, by the way, are of a similar standard to the ones that you will find in the assessment. Okay, so let's what we've got. There's one particular one that's really naughty. We'll leave that one till last. Now we've got a couple here. Right, let's do this one. So determine whether this system of forces is in equilibrium. Right then, so if my system of forces is in equilibrium, then the sum of all the vertical components and the sum of all the horizontal components would both equal 0. If that's the case, the thing's not going anywhere, all the forces balance, it must be in equilibrium. So I can either do the full, calculate the full, both sets of force elements, or just do one. And as soon as I prove that either of these is not 0, then I've also proven that this system of forces is not in equilibrium. So let's consider the Well, the easiest one to do would be to do these ones, because the 2000 newtons there is vertically straight up, and so it hasn't got a horizontal component at all. So if we want to do the horizontal ones, well, it'd be a fairly straightforward way of doing it. So let's consider what the FHs are going to be. And again, the horizontal, that's going to be the positive direction, and sorry, horizontal, that's going to be the positive direction, and vertical, that's going to be the positive direction straight up. So horizontal forces then, we've got this 1500. What would be the horizontal component of that force? So it'll be a +1 because it's going in the plus direction. It would be 1500 multiplied by what?
Cos 40.
Yep, cosine of 40, because that's the direction, that's the force that we're resolving. It's going up there, that's the direction we want to resolve it into. It's going through that 40-degree angle. Through the angle, you use cos. Okay. The 1000 Newton force down here is actually going in the opposite direction, so that'd be negative, because if I resolve that into that direction there, it's going in the wrong direction. It's going in the negative direction. So let's take away 1000. What would be multiplied by what?
Sine 30.
Ah, you see, you're falling into my trap. Are you going through the angle or away from the angle?
Away.
That 30 degrees, you're resolving this 1000 Newton force in that direction there to find what this component is. So are you going through the angle or are you going away from the angle? Through it. If you go through the angle, what do you use, cosine or sine? Cosine. So cosine of 30. Exactly the same principle we did with this one. That's why I said that those rules for calculating the different components aren't hard and fast. It depends what angle you know as to what trig ratio you put in. Now you can, if you want to, if you get confused, you can draw the triangle and put your hypotenuse, your opposite and your adjacent in there, and you can work out which ratio you need to use, which trig ratio. But it's easier if you just remember, if you go through the angle it's cosine, or away from the angle it's sine. It's a rule of thumb, but a very useful one. So what we've got there is the sum of the horizontal components are going to be force acting in this direction, or a component of that force acting in this direction, equal to 1500 cos 40, and then another one acting in this direction that's 1000 cos 30. And if this is balanced, if this is going to equal 0, then it's in equilibrium. So let's see. So work that out for me. Does 1500 cos 40 take away 1000 cos 30 equals 0? Or if not, what does it equal?
I don't get 0.
What does that mean then? If it's not 0, what can we say about this system? Determine whether this system of forces is in equilibrium. Is it or isn't it?
It's not.
It's not. Okay, so 866. So we know then that the sum of the horizontal forces are going to be there or thereabouts. 1149, take away 866, 283 newtons. So we know for a fact that this thing's not in equilibrium, because the sum of the horizontal components is not equal to 0, and that would be enough to prove that. You could just stay there if you wanted to, but because we're sort of demonstrating understanding, or trying to give some understanding, what I'd like you to do, please, is to calculate the sum of all the vertical forces, and that would start off with 2000 newtons in the vertical direction, and all of that's acting in vertically. There is no angle to concern yourself with. And then it would be take away 1,000 times something, take away 1,500 times something. So what would be the two vertical components of this force and this force? Fill in the blanks and then come up with an answer for me, please. What you've got to think about there is whether I'm going to use the sine of the angle or the cosine of the angle. So, anyone want to chip in and complete that line of working for me, even if you've not got an answer yet?
Is it sine? Because you're going away.
It is. So the 1,000 here will be going through this way. We're resolving into this direction. So we're coming away from that 30 degrees. So that would be sine of 30. And this 1,500 here, again, we're swinging it down this way, away from the known angle again. So if you go away from the angle, it's sine. So we're going to have sine 40. And then it's a case of that, take away that, take away that. I don't know what the answer is, so you'd have to tell me. But I'm fairly sure that it will be not be zero. And so we've conclusively proved then that this thing is definitely not anywhere near in equilibrium.
I got
1,535.8. Let's call it 36. Did anyone get that?
I've been getting the wrong answers for near enough everything, so I'm not sure if it's my calculator or not.
You're not in radians mode or anything daft, are you?
I don't think so, no. Actually, yeah, it might be.
Because that's the classic. So if you've got the same calculator as mine, then if you go into the mode setup button, or is it that one? No, it's not, I don't think. It's shift mode setup button, and then make sure you press 3, and then there should be a little D somewhere in your screen. If you do shift mode setup 4, then you get an R for radians, or shift mode setup 5, you get a G. I don't know what that even means though. Do you want to be in 3 anyway? Make sure you've got that little D in there.
Okay, I got 535.
1,535.
No. Just 535.89.
Is that what you got, Byron? Or did I make that extra 1,000 up by not listening?
No, that's what I got.
Okay, so let's figure out which ones of us is telling the truth. So we've got 1,000 times the sine of 30, which is 500. So we've got 2,000 minus 500 minus 1,500 times the sine of 40. Which is 964. So I think you're right. Yeah, I think you're right, Daniel. So do you see this line of working down here, Byron? So you've got 1,000 sine 30 is 500, 1,500 sine 40 is 964. So if you take both of those away from 2,000, that's what we're after. So that the 5, whatever it's the other guys were saying, seems to be a more reasonable answer. Do you dream it? Didn't scream out as being completely impossible, that, as an answer. But that's more like it. Okay, so you know for a fact that those aren't in equilibrium, and actually you could, if you wanted to, go on and calculate. That's the vertical one, so that'd be 536, and that's the horizontal one would be 283. You could go and calculate what the resultant was, and then you calculate what the equilibrium was. So just determine whether the system of forces is in equilibrium, and it's not, and then if the question went on to say, if it's not, find out what the equilibrium would be, then you could do that. But yeah, so that's just a way of resolving forces again, turning three forces into this system of two forces, and for the reason this time not to calculate the resultant, but just to say that these two rules that need to be fulfilled for this system to be in equilibrium aren't fulfilled because we have got some force. They're not the balanced and sum to zero, so they're not therefore in equilibrium. Right, now we're building up to the really difficult one. This one not so much, but it takes some thinking about. So in this case we've got a system that's got two forces that are unknown, and we need to calculate both of those unknown forces. So again, we're going to do exactly the same thing. We're going to separate the system and all the different forces into their horizontal and vertical components, and then we're going to be able to work out, hopefully somehow, what FA and FB are. So first thing we're going to need to do is determine what the sum of all the horizontal forces are. And let's do verticals first, and then we've got, so vertically speaking, big one there, we've got FA, this unknown force, FA. FB here, because that's purely horizontal, there will be no vertical component to it, so it has no effect in the vertical direction. This one, and again remember we've got upwards as being positive and left to right being positive. This one down here, this is going to be acting downwards in the negative direction, so that is going to be negative 1200, and I'm actually going through that 45-degree angle. So if I go through the angle, it's cosine. And this 1200 Newton one here too is also going to have an effect in this direction, and so the 1200 cos 45, and we take away another 1200, and again it's going through the angle, running out of paper, cos 45. And from that we know that if this thing is in equilibrium, which is part of the question actually, it is in equilibrium, and it did state that, or would have stated that in the question had it been written out in full. So we know, because it's in equilibrium, as the system is in equilibrium, then we know that the sum of all of those vertical components equals 0. So we know that 0 equals this unknown force minus 1200 cosine 45 minus 1200 cosine 45 again, because they just happen to be same size and in directions that are similar angles. So if I want to just rearrange that slightly, then I can say that FA, if I'm going to separate these to both sides, I would add that one to that side, add that one to that side, so I've got 1200 cos 45 add 1200 cos 45. Does that make sense? Because that's now 0 at that side, so I'm actually taking these two to that side, but I'm writing FA equals. Deliberately designed to confuse you a little bit maybe, but if we separate it out like that, these two become positive, which kind of makes sense because we know that FA is going to have to be positive to balance these forces that are both going vertically downwards. So calculate what FA is for me, please. 1,697 newtons. So did I. Right, so we know that FA equals 697. So we've been able to do that by knowing the system's in equilibrium and resolving all the forces that are in the vertical plane. Okay. Now, what I'd like you to do now is find the sum of all the horizontal forces. And that is going to equal FB, which is in the positive direction. And then we're going to add the horizontal component of this force and take away the horizontal component of that force because it's going in the opposite direction. So, complete that sum and then work out what FB is, please. So what have you got to complete that sum now? What's your line of working look like? Do you want to tell me, Drew? Okay, so we've got horizontal components now, so we want to calculate the horizontal components of these two forces. Okay, so I'm going to take that force and I'm going to wind it that way to find out the effect it has in that direction. So am I going away from the angle that I know, or am I going through the angle that I know when I resolve that in that direction? You're going away from it. So if I'm going away from it, do I use the cosine of the angle or the sine of the angle? No. Sine, yes, sine is away, cosine is through. Okay, so what I would say is that this one is 1200 times the sine of 45 would get me the horizontal component of that one. And this one is going to be going in the opposite direction. So this one's going in the positive direction, this one's going in the negative direction, but it's going to have the same magnitude because it's at the same angle and the same force. So this one is take away 1200 sine 45. So again, then we know that as the system is in equilibrium, the sum of FH's equals 0. So we know that 0 equals FB plus 1200 sine 45, take away 1200 sine 45. So what do I get if I add, if I take away 1200 sine 45 from 1200 sine 45? Well, I get 0, don't I? So I know that actually FB in this instance is 0 because these two forces already balance, which kind of makes sense if you think about it, because they're acting at the same angle and the same magnitude but in opposite directions. So it makes sense that the horizontal components of these two forces will balance. And if these balance, then this system's in equilibrium, and so FB must equal 0. Because if FB doesn't equal 0, it'll be unbalancing this thing and spoiling the equilibrium, and it'll start moving somewhere. But don't be surprised sometimes if you do get a 0 answer. Have a look at the geometry and often it will make sense. Anyone else get that? Understand that? Not get that? Okay. Trixie woo, eh? Now, we won't be going on for much longer, but this one And you can, I want you to go over some of these as well. And if we do get this video up and running, it might go on YouTube or something, because the lighting's all going rubbish now because we're in the office window. Just stick some light on the subject, whether that's helped or not. Not really. Just pull the blinds down. This might be a bit better. That's my microphone cable getting in the way. Okay, so now we've got a system where I have to find FA and FB, and this is dead complicated because we've got two unknown forces, FA and FB, and this one's a bit more difficult to sort out. So let's take it one step at a time and have a look at how these angles work. So just like before, I've been given some fairly major angles, but not the individual angles that I may find a bit more useful. So 45 degrees from the vertical, that's fine. I've got 70 degrees there from the vertical, that's fine. What I could do with is some angle for FA and FB that ties that to a horizontal or a vertical, because this distance between two forces is not a right lot of use to me really. So taking into account that these are 90-degree quadrants, I want to find, well, what are the missing angles? So split that 70 up and split that 95 up. So what would that angle there be, for instance? It would, because overall it's 90 and this is 70. And if that's the case, what's this angle? 50 again, because we know that that 20 and that 50 equal that 70. Along the other side, what's that missing angle? Yep. And lastly, that missing angle. Yep. Right. So we can almost ignore those now. They're the ones that are given in the question, but now we've got some more useful angles that tie everything into these vertical and horizontal directions. Now we've got quite a lot of forces and lots of things going on here, so the working is going to get a bit complicated, but it's not difficult, it's just more of it. So again, likewise, we're just going to calculate what the sum of the, which one should we do first, the vertical components are. So some of the vertical components. So let's consider force B. So we've got FB. If I resolve that into the vertical component there, then that angle's 50. So I'm going away from that angle, so I can use sine, and the angle's 50 as well. So it's going to be FB sine 50. By the way, if you carry on working all these angles out, you could say, of course, that that angle there is now 40, because that 50 and the 40 must equal the 90. Likewise there, that's a 40. So you can work all of those angles out if you really want to, and that gives you some flexibility on how you can apply your trigonometry, because you will find that I can either say that it's FB sine 50 because I'm moving away from 50, or it's FB cosine 40 because I'm moving through the 40, and sine of 50 is the same as the cosine of 40. That's how they work. That's how sines and cosines relate to each other. So you can do that if you want to, but you'll always be working with either going through the angle or going away from an angle. Just make sure that you use sine for when you move away from an angle and cosine when you move through an angle, and it doesn't really matter which angle you use as long as you follow those rules. So that's the vertical component of that one. The vertical component of FA, that's going to be going up as well, so that's going to be positive. So that's FA, and I can either say, if I want, that it's FA times the sine of 50 or the cosine of 40, because they work out to be the same thing. So we'll FA or sine of 50, since we've done that before. And the rest of it, I'm running out of space, but these are going to be takeaways now. They're going to be negatives because these two forces both have vertical components going downwards. So that's in the negative direction. And I've got 60 kilonewtons, and I'll use cosine 45. Cosine 45. Now in that case, it doesn't matter which you use. You can use cosine 45 through the angle or sine 45 away from that angle, because both angles are the same, because cos 45 equals sine 45 because of how their cosine and cosine relate to each other. So again, that's a bit more straightforward. It's more difficult to get wrong. You can't choose the wrong one because they both work. And then we've got the 40 kilonewtons here again. That's going to be going in the negative direction downwards. So we've got 40, we'll use the cosine again, going through that 70-degree angle. Okay. Now we can sort of simplify that a little bit, and we can turn that into numbers. And we'll do that in a second. In fact, I'll do that. I'll turn that into numbers while you go and have a look at what the horizontal ones are. Equals that. So we're going to follow a very similar process, but instead of resolving things in the vertical direction, we're going to be resolving things into the horizontal direction. So FA is going to be positive this way, and that 40 kilonewtons is going to be positive this way, and that's going to be negative FB somewhere that way, and negative 60 somewhere that way. But write that style out using the right angles and the right trig ratios, and then we'll come and have a look at that in a second. I'm just going to replace all the cosines and numbers in this thing with actual numbers while you do that. So that is going to equal 766 FB plus 0.766 FA minus 56.106. Okay, so what's that going to look like? Start at FB, so what's the horizontal component of FB going to look like? be a minus.
Minus FB cos 50.
Yep. Because it's through the angle, it's cosine, or you could have said it's away from the 40-degree angle and used sine 40. So either minus FB cos 50 or minus FB sine 40 would be fine. And then we'll go clockwise, shall we? Add FA, and what we've got for FA.
Cos 50.
Same thing again, yeah, cos 50. And then we've got another add of this 40, and that's 40 is going to be cosine of 20, or the sine of 70, or the cosine of 20, the same thing. And then we're going to have another negative one, which is this 60, and it's 60 times, if we're going through the angle, it's cos of 45, or we're going away from the angle, it's sine of 45, and cos of 45 and sine of 45 are the same thing, so it doesn't really matter which one we use. So I'm going to call it cos of 45. And then what we're going to do is do what I've just done up here and turn this thing into some real numbers. So we have got f of h. So we have got, let's have it in the same order that we have those in. So we've got minus FB and the cosine of 50. I don't know whether this example is going to work very well. Is 0.643, let's call it, plus FA times 0.643, because it's the same because of 50, plus what is 40 times the cosine of 20, 37.59, and then take away 60 times the cosine of 45. $42.43. Okay, so that leaves us with 37.59. So tell me, it is getting complicated now. 42.43 equals. So that leaves us with the sum of the horizontal components equals minus FB times 0.643 plus FA times 0.643 minus 4.84. Okay, so we also know that because this thing's in an equilibrium, then the sum of the FH's is going to be equal to 0. So we know that that is actually 0. 0 equals minus FB times 0.643 plus FA times 0.643 minus 4.84. Right, so lots of numbers in there, but what we've got now are two formulae. That one. So that's all the difficult resolving of forces bit done. And now we've got an entirely different question. What I've got here are two equations in two unknowns, otherwise known as simultaneous equations. Hooray! So we've done all the hard bit of the geometry and the resolving the forces and the directions and the cosines and sines, and I've ended up with two quite horrible looking formulae that I will now need to solve using one of the techniques that we've done in the past for solving simultaneous equations. And the one I want to use, while I just go and get some more paper, is elimination. So, elimination. So what I'm going to do is I'm going to rewrite these again, and we're going to sort of change the emphasis of this now from a problem about resolving forces, we've done that bit, into a problem about solving simultaneous equations. So I'm going to write these simultaneous equations out again. And we might as well leave them equal to 0 for the time being. So we've got 0 equals 0.766 FB plus 0.766 FA minus 56.106. And I'm going to call that equation 1. Okay, we've got equation 2 as well, and that came from our from the horizontal forces. So that comes out at minus 0.643 times FB plus 0.643 FA minus, see, loads of opportunities here to cock this up. So now we've got our two formulas for our two simultaneous equations. Now if I'm going to use elimination for these, I'm going to have to multiply one or other of these by a factor that means that what I want is for two of these terms to be the same. So I need to multiply this line by a factor that's going to turn 0.643 into 0.766. Okay, so if I say 0.643 actually that's going to need to grow bigger, isn't it? So it's 0.766, divide that by 0.643, and I get a number that is 1.19. So if I multiply number 2 by a factor, and that factor is 0.766 divided by 0.643, and that equals 1.191, then what should happen is that the numbers in this increase to match the numbers in this. Okay then, so let's do that. So multiply equation 2 by 1.191. So I've got 0 equals, and I've got, now this should work, I'm just checking it on my calculator, 0.643 multiplied by 1.191 equals, as near as we're going to get to, minus 0.766, and that's going to be plus, that's going to be FB, plus 0.766 FA minus, now I've got to multiply that 4.84 multiplied by 1.91, hang on, sausage fingers, 4.84 times 1.191, so that comes to 5.764. So I'm going to call this one equation 3. So we found our multiplying factor, that if we multiply this line by this factor, then these numbers will change and become very close to these numbers, if not the same as these numbers. And then that's my adjusted equation 2. And what I'm going to do is I'm going to take that one and equation 1 and then add them up. So you'll notice that this is minus 0.766 FB and equation 1's got a plus 0.766 FB, so if I add them two together, those two terms will cancel each other out. So we've got 0 equals, it's complicated this, isn't it, 0.766 FB, so this is equation 1 I'm bringing down, plus 0.766 FA minus 56.106. Right, so I'm going to add these two lines up now. So this is going to be 3 add equation 1. So 0 add 0 is 0. Minus whatever that is FB add whatever that is FB is going to be 0. And then we're adding those two together. So that is going to be 0.766 times 2, which is 1.532 FA, and that's going to equal those two things added together. So if you add those together, they're just going to get even more negative. So we've got minus 5.764 add minus 56.106 is minus 61.87. That shouldn't be an equal sign, that should be a minus sign. Now we can find out what FA is, because we've got one equation in one unknown, and if we rearrange it, we know this end's equal to 0, that 0 will disappear, so that'll disappear, that'll disappear. If I rearrange this, basically I've got 0 is 1.532 times FA minus 61.87, so I know that 61.87 equals 1.532 FA, and so I know that FA, crikey, equals 61.87 divided by 1.532. Whew, tired now. 1.532 equals 40.39, and what was my original layout like? Kilonewtons. Right, so does that make sense? Well, it's positive, which is acting in the positive direction, so that kind of makes sense, doesn't it? So that's my magnitude of FA sorted out. Then what I would do is, in the age-old tradition of simultaneous equations, go and stick FA equals that into one of these up here and calculate what FB is. So that's a horrible, horrible, complicated, nasty question, but still not finished because we've still not found FB. But there is a question very similar to this in your assessment. Then substitute FA into 1 to find FB. Crikey Moses. So that's what we need to do. That's the type, as I say, the type of question that's in the assessment. It is complicated. It's because of the number of forces that are involved, and the fact that it's not simply just forces that are involved. You've also got to start doing simultaneous equations as well. Tricksy. So you'll need to have a look through that. Last thing today then is go and substitute FA equals 40.39 kilonewtons into any of the above and find what FB is for me, and then we'll call it a day. It's a three pieces of paper question to answer that one. You're still awake? So I'm going to do it on a bit of paper. You're going to work it out and tell me the answer. So all you're doing is you're substituting FA equals 40.39, and you're substituting that into one or the other of the ones at the top. So we're going to have I'm going to substitute that into equation 1, so I end up with 0 equals 0.766 FB plus 0.766 times 40.39 minus 56.106. And we need to rearrange that to find FB. So what does that work to be? So that's 0.766 multiplied by 40.39 equals, take away 56.106 equals that. So we've got 0 equals 0.766 FB minus 25.167. So FB equals 25.167 divided by 0.766, which is 32.86 kilonewtons. You get that? So according to my calculations, that is that, and that is that, and that took 3 pages of working. Now what I'd be very tempted to do now to make sure that I've got these right, because that is just working from scratch, is to then go and put those values back into the original formula to make sure that they actually work and do sum to 0. In both of those. You never know, we might actually got it right at that. Okay, so that one's a bit naughty. What I suggest you do is, well, I'll try and get a copy of this video out to you. Have a go at them as I've introduced them. Get a bit of paper out, see if you can follow the working. If you can't, then just incrementally play a bit more of the video and catch up a bit and try and follow what I've done. So just to recap that last one there then, because that is by far the most complicated one. It involves you resolving the forces into vertical and horizontal components. You know, because it's in equilibrium, that they will equal 0 in the end. So you end up with 2 equations that are simultaneous equations, both have FAs and FBs in them. Then you need to set up your simultaneous equations for elimination. So you need to find this sort of multiplier, this common denominatory type thing, which will allow you to multiply one line of this in order for these the prefix of FB or FA to be the same, so that when you add them up or take them away, they disappear. So in this instance here, we've multiplied 2 by 1.191, and that gives us this line 3 here. And then we've taken 1 and brought it down, and we've added these up. And we're adding them up because this is already negative and that's positive. If that was positive and that was positive, then we'd take them away from each other. But because they're opposite anyway, if I add that to that, then the term in FB will disappear and will leave me with just terms in FA. And once I've got FA on its own, I can calculate what it is. So stick that in, calculate what FA is, then substitute FA back into one of the original formulae that we worked out to find out what FB is. Tricky. Okay, anyone desperately lost? I suppose probably there is. So it's down to you to go and have a bigger look at it, because it's not going to get any easier, and the only way to tackle these things is by going and giving them a go. Is that all right? Okay. So like I say, next time, the first week before Easter, it'd be nice if we could do the assessment for this, but you may not be ready for it. We might have to do some more practice questions or a practice paper, because there's no point in hiding. If you can't do this, if you don't get it, then we need to get you into a situation where you're more comfortable with it so you can pass the assessment. And having said that, I'll say ta-ra. Who's missing? So Logan's missing, and who's the other one? Logan and Harry. So Logan and Harry are assuming they were all on strike, I suppose. Didn't have the common sense to get in touch like Byron did. Okay, so I'll see you next time, guys. I hope that wasn't too tedious. I found it quite entertaining, but I'm a bit weird. You comfortable with any of that, Kamal, or do you hate it all? Okay, cool. Yeah, that last one is a difficult one. It's just lots of it, that's all. It's not particularly any more difficult than the others, just a lot of it. Right, have a nice weekend, guys, and I'll see you later.
Cheers. Thank you.
Bye. Oh, by the way, stop what you're doing. Don't leave yet. Oh, you're leaving already. Oh.
It's just me.
Okay, have you filled out that thing that I asked you to fill out? Right, cool. If you just come back on, Byron, can you? I dropped a message to fill out some sort of review thing. Oh, he's gone again. If you have, that'd be great if you could fill out as many as you can, please.
I'll ask him out if he has.
If you would do, that'd be great. Cheers. See you next time. Bye.